Think about it. Every single day, we rely on scientific studies to tell us how to live a little healthier, think a little sharper, and basically just understand human behavior. We read the headlines, we trust the data, and we assume the methodology behind it all is rock solid. But what if the very blueprints of these studies contain a hidden trap? What if the way researchers actually design their experiments is completely distorting the results? Well, today, we're exploring a fascinating academic detective story to uncover exactly how some of the absolute most popular study designs might be secretly skewing our understanding of psychology.
Okay, let's dive into this. Welcome to today's Explainer. If you love understanding how things work behind the scenes, you are definitely in the right place. We're going to explore the mechanics of statistical methodology and scientific integrity, really peeling back the curtain on how researchers set up their studies. Because, as it turns out, getting reliable data isn't just about asking the right questions, it's about avoiding some incredibly sneaky mathematical pitfalls.
To really grasp the problem here, we first have to look at the absolute biggest hurdle every researcher faces, which is recruiting participants. I mean, it takes time, it takes money, and it takes a ton of effort. Now, in a standard parallel study, researchers need totally separate groups for each condition. So if you want to test a new therapy versus a placebo, you literally need Group A and Group B. But there's a popular alternative that many consider a total holy grail, and that's the crossover study. In a crossover design, the exact same participants just recycle through all the conditions. You don't need a Group A and a Group B. Instead, your participants act as their own control group, so they experience both the therapy and the placebo at different times.
Now you might be wondering, why do researchers love this so much? Well, it all boils down to a concept called statistical power. Basically, that's a study's ability to detect an existing effect if it's really genuinely there. Because crossover designs recycle those same participants, there's this very common yet honestly kind of arbitrary rule of thumb that floats around the scientific community. Researchers just assume a crossover design can achieve the exact same statistical power using only half the sample size of a parallel study. So less recruiting, fewer resources, but the same powerful results. Sounds like a massive win, right?
Let's walk through exactly how this works in a standard 2x2 randomized crossover clinical trial. Imagine we're testing a brand new pain medication. In step 1, Group A gets the active pain med, while Group B gets a placebo. Then, in step 2, a little time passes. Finally, in step 3, the groups swap. Group A gets the placebo, and Group B gets the active med. Everyone gets everything. On paper, this design is brilliantly efficient, it's incredibly flexible, but just when this setup seems totally perfect, a hidden threat emerges from the shadows, and it's a complication that can literally invalidate the entire set of results if researchers aren't incredibly careful.
Section 1. The villain, otherwise known as the carryover effect. This hidden threat is what researchers call the carryover effect. So the crucial point here is that a treatment doesn't always just magically stop working the very second an observation period ends. The carryover effect is the residual influence of a study treatment on whatever treatment comes next. If a drug or therapy lingers in a participant's system, it completely ruins their baseline for the next condition.
To really picture this, just imagine taking an incredibly strong active pain medication in period 1 of our study. Now, period 1 ends, and we move to period 2, where you're supposed to take the placebo. But what if that drug from period 1 is still physically active in your bloodstream? You're taking a completely useless sugar pill, but you still feel amazing because of the first drug. It's absurd, right? The initial condition is now having this additive, confounding influence on your subsequent research outcomes. The placebo test is totally compromised.
The statistical vulnerabilities caused by this are just massive. It creates that additive confounding influence we just talked about. Even worse, it can render those subsequent placebo treatments completely useless. And here is the absolutely vital detail. This bias is exacerbated when data is non-normally distributed. As noted in our source material, which references a massive review of standard behavioral measures, psychological data is almost never normally distributed. It's messy, it's complex, and that means behavioral crossover studies are highly susceptible to these devastating carryover errors.
Which brings us to Section 2, the shield, the washout period. Now, researchers are smart, and they came up with a clever solution for this called the washout period. It's exactly what it sounds like. It's the dedicated time researchers wait between conditions to let the effects of the prior treatment completely wash out of the participant's system. The whole goal of the washout period is to safely and completely return the participant to their absolute baseline state before the next treatment even begins.
But the real question is, does this shield actually work in practice? Well, to find out, we're drawing directly on a comprehensive dissertation from researcher Kyle Moxley at Wayne State University.
Moxley did a massive deep dive into peer-reviewed psychology research just to see if these crossover designs and washout periods are actually being used with rigorous scientific precision, or if they're just masking hidden flaws.
Moxley points out the immense paradox of the washout period here. Adding a pause seems logical, sure, but it introduces a whole host of new threats. First off, it extends the total study time significantly. And because the study takes longer, you increase the risk of what are called period effects, which are basically just natural changes in a participant over time. You also face a much higher likelihood of participant dropout, because people just get tired of waiting around and quit the study. But perhaps most concerning of all, the length of this washout period is usually chosen completely arbitrarily, before the data collection even begins.
Section 3. The investigation. 10 whole years of data. To see how researchers are handling this paradox out in the real world, Moxley's investigation looked at a full decade of data. Using some really robust inclusion criteria, covering the years 2010 to 2020, the investigation identified exactly 107 peer-reviewed articles from across the psychological and behavioral sciences that actually utilized these specific crossover designs and reported their washout periods.
And from those 107 articles, the scope of the data just became massive. The review extracted 988 individual crossover analyses. Of those, 752 were statistically significant. I mean, we're not talking about a small sample here. This was a sweeping look at a decade of established, peer-reviewed science.
Now, what's really interesting about this slide is the fascinating trend that emerged across this massive landscape of 988 analyses. The review found an average median effect size of 0.52. But honestly, the real story isn't just that number, it's how the washout periods correlated with it.
Just take a look at this shocking disparity. This breakdown shows the washout times used by researchers converted into seconds so we can easily compare them. Now keep in mind, 604,800 seconds is exactly 7 days. You can see that for very small, and medium effect sizes, the median washout period was exactly 1 week. But look at the mean washouts. The averages just range wildly into the millions of seconds. Washout times across the literature ranged from literally just 60 seconds all the way up to over a year. The data starkly reveals that in psychology, researchers are basically throwing darts at a calendar. They use a week, or a day, or 10 minutes, and they rarely ever test if the carryover effect is actually gone.
All right, Section 4. The verdict on washout.
The investigation utilized a non-parametric statistical tool, a really specialized test designed specifically for this kind of messy data called a Kruskal-Wallis test, to compare the results. And here is the bombshell finding. The amount of time arbitrarily chosen for a washout period actually significantly influences the study's ability to detect an effect. Let that sink in. The duration of the pause literally changes the magnitude of the result.
And this brilliantly illustrates the tightrope researchers are walking, often completely blindfolded. Because if you guess a washout period and it's too short, you quickly introduce carryover bias, and boom, your data is compromised. But if you guess a washout period and it's too long, you introduce period effects, participant dropout, and you severely kill your statistical power. Without mathematically justifying that washout time, you're literally risking the entire integrity of the experiment. To sum it all up, the source material actually states it perfectly. Arbitrary approaches to washout length may have consequences leading to reduced statistical power. It's a stark reality, guys. Poor washout planning destroys the exact statistical advantage, that increased power that the crossover design was supposed to provide in the first place. So, let's move to our key takeaways for today and see how this all builds together. First, crossover designs, while they are amazing in fields like pharmacology, where drug half-lives are actually known, they're incredibly fragile in psychology. Second, washout periods in the behavioral sciences are rarely tested or justified. They are mostly just arbitrary guesses. Third, the potential power loss from an incorrect washout period can entirely cancel out the advantage of using a crossover design over a standard parallel study. The ultimate lesson here is that researchers absolutely must balance the uncertainty of carryover with the severe risks of washout by using much greater methodological precision. It leaves us with a pretty critical question to consider the next time we read a headline about some groundbreaking behavioral study. Think about it. If researchers are using participants as their own control group, but they don't actually know how long a psychological effect lasts before it washes out, can we truly trust the power of their results? It's just a great reminder that good science isn't just about the answers we find, it's about rigorously questioning the methods we use to find them. Thanks so much for joining me for this explainer, and keep asking those tough questions.